So the idea of randomized block design is just slightly different. I wouldn't put it in the same category as one-way and two-way ANOVA, but rather as an optimization technique. Because whenever you don't use block design, you end up going back to the basics, which is using it as a one-way ANOVA or two-way ANOVA. So in randomized block design, imagine in the previous one-way and two-way ANOVA designs that we've seen, you treat each treatment as a full. So take a look here on the right, you're going to see three different treatments, or treatment number 1, treatment number 2, and treatment number 3 under the same factor. Every single experimental observation that you have is treated into one group. In randomized block design, you're grouping them into smaller groups, and in cases where you identify some extreme numbers, you're able to take it out. So this optimization technique allows you to capture a little bit more variability and also to reduce the errors in case you identify something that's extreme. So in other words, it has a smaller within group variability. We're going from the disadvantage of a mean is that whenever you have outliers or extreme numbers, it is being pooled that way, but in block design, it will not because it's in smaller packages. The blocking will increase a higher F-test if it is effective. So in other words, before the experiment, the subjects are divided into homogeneous groups, blocks according to some characteristics known to be correlated to the dependent variable. When we talk about stratified sampling, it's as if we were to categorize everybody by their hair color. You can have blonde color, red color, brown color, black color. And depending on each group, there may be a different population value. In stratified sampling, I would put all of the hair colors into different categories. And out of each category, we will pool 5 people. Stratified sampling will allow you to draw the same value without being relative to the number of the true population. So this is what blocking will do, and whenever we talk about different researchers or different people, well, we're trying to draw equal sample sizes from one treatment to another. This will reduce your bias. It will also reduce your error terms because you have a much more controlled environment. Let's take a look at this example. It doesn't have a big context. The idea is very simple. You have 10 subjects that are interviewed by 5 research assistants, and each assistant will be using different types of treatments to interview. So you can have one treatment where you're very nice, one treatment where you give a hug, one treatment where you give a handshake, one treatment where you don't say anything, and one treatment where you act as a third person, for example. And we're going to answer the following question. Find the marginal means of each treatment condition based on this data set above. Create a line plot for all 5 blocks. So previously we've seen what an interaction plot is, and using the marginal means, you're able to recreate a line plot just to look at a graphical method, just to look at what is going on and whether there are some types of interaction, there's anything going on. 3, here are the 2 outputs. So I'll be showing you 2 outputs, one with blocking and one without blocking. We're going to see the differences between the 2. And from then, we're going to vary that data set to see whenever blocking would be useful. So starting off with this first interview responses. Okay, these are I believe scores that are given from the interview, and under each of the treatments, there were 2 people who were interviewed by the same researcher under the same treatment. With this, you can calculate your marginal means for each of the treatments, and then we'll be able to create a plot. Inside the blocks, you're looking for 5 researchers who are trained the same way, and hopefully we're trying to create a homogeneous environment. So if there's one person who who is slightly different or treating people slightly differently will be able to see it. So based on the data set above, create a line plot for all 5 blocks. Here is the line plot. And I'm showing you the marginal means. You'll see that different treatments, for example, 4 has relatively higher response rate, 5 lowers a little bit. However, there's nothing that strikes you. Everything is intertwined and it looks pretty okay. If you want to run it in SAS EG, you can follow these following steps, and there are also video tutorials to help you out. So based on these 2 outputs, what can you say? One was with blocking, and I will point it out for you. This one is with blocking, which is A, and the one on the right is without blocking. First of all, we have to check out the model. Is the model significant? In this case, you have a significant model in both sides. However, B is a little bit more significant. That's what we can say. On the other hand, you'll see that the R-square for blocking is much higher because it's repeated and there's less variability. Therefore, the 5 researchers are considered as 5 times the experiment, whereas without the blocking, they would be considered at only 1. And that would explain your R-square 0.36. In reality, B is what actually explains. But because you're using blocking and you're repeating the experiment over and over again, your R-square gets increased a little bit. In other words, a little bit inflated. However, because of the lack of bias and a bit more control, your root C, which is your error term of the entire model, is reduced slightly. What else? If you take a look at the degrees of freedom, for B, for the model B, you will see the model is based on 4 different, which is 5 different treatments, 5 minus 1. Whereas in this case, it's broken down into different compartments. So your degrees of freedom is much higher. Now looking at the different types, whether with blocking or only with treatment, the block here, if you look at the F value of 1.86, is insignificant. What does that mean? An insignificant F means that your blocking was not effective. So by default, we're going to use blocking every single time, just to control and have a little bit less bias. But your blocking was not effective, as in it didn't help. As for treatments, your treatment was very significant, meaning that there is a significant difference between the means from one treatment to another, which is usually what you're looking for whenever you're running an experimental design. And finally, this interaction term between blocking and the treatment. I know that in two-way ANOVA, you're looking for an interaction between 2 different factors so that you can conclude that the black big car generates more sales. In this case, the usefulness of blocking is to repeat, and therefore you do not want to look for differences from one block to another. The fact that the blocking here doesn't work is a good thing, because it means that you have low bias and you have high control and homogeneous sample. So that makes sense that the interaction is not valid here. On the other hand, if you take a look at only the treatment will generate the exact same thing as value for the entire model, because it's treated as a one-way ANOVA, and it shows you that there are differences from one treatment to another. So these are the differences between A and B. In this case, although blocking is not necessary, it does help protect. But you have to be aware that your R-square is much higher for a certain reason. It's the reason that you're running this experiment over and over again. And the real explanation of your independent variable in this case is actually 0.3670. 0.367. Here's a representation. I usually pull either a box plot or any type of plots just to see the overview, and you'll see that each treatment from one block to another, actually going from block 1, 2, 3, 4, 5, doesn't have a drastic difference, which is a good thing because it keeps the entire sample much more homogeneous. If you look at the grouping, all blocks are grouped under the same group of A, and under your 2 key, there's nothing identified as having a main difference. This is safe in a sense. It also means that your blocking was not effective. It did not help you protect. If you take a look at the differences from one treatment to another, going from treatment 1 to 5, then you will see slight differences, but based on the box plot, we can't tell much. The only thing we can say is that from one treatment to another, there may be some changes. So therefore, you can dig a little bit deeper by looking at the groupings. Whenever we look at the groupings, this is telling you, well, which type of treatments are generating similar sales or similar performances. So under the grouping A, it tells you that 4 and 5 are treated the same way. Whether you use treatment 4 or treatment 5, it will generate the same performances for you. And the same way for grouping B, if you're working with 5, 1, and 3, it'll generate for you the same performances. And for C, 1, 3, and 2, these methods of interviewing will generate the same type of responses. You can even go in further details if you would like to know, well, which response or which type of interviewing is more effective. You'll see here that 4 and 5 is a little bit more effective than 1 and 3 and even 2, based on their means. You'll also be able to identify those that are strictly different from each other. In this case, you have 1 and 4, 2 and 4, 2 and 5, 3 and 4, 4 and 1, 4 and 2, 4 and 3, and 5 and 2. Sometimes it's a little bit hard to look at this and create a summary. Therefore, SASEG does create a summary for you.